Welcome to Tungal Online Classes. In previous video, we had discussed the concept of fluid, pressure exerted on a liquid column. After that, the variation of a pressure with a depth, right? So today, we are going to discuss the new concept that is Pascal's law. So that is Pascal's law. So then, what is the statement of a Pascal's law? The statement is, if an external pressure is applied to any enclosed liquid, is transmitted uniformly in all the direction, So that is the statement of a Pascal's law. Okay, see here, the statement is, if an external pressure is applied to any enclosed liquid is transmitted uniformly in all the directions. So this is the statement of a Pascal's law. If an external pressure is applied to any enclosed liquid or fluid is transmitted uniformly in all the directions. See the general example here. So consider the two syringe. So consider this is one syringe. Consider the two syringe, and these two syringes are connected with the help of a pipe. So afterwards, we are exerting some amount of force on this piston. So consider this is one syringe and this is another syringe, and these two syringes are connecting with the help of the pipe. After that, we are applying some amount of force on this piston, right? So due to this force, this piston, it is moved to the new position, right? So in that case, this piston exerting some amount of force on the fluid. So that pressure, it is distributed in all the direction and it exerts on the second piston. So due to that pressure, this piston, it is moving in outward direction. Okay, see here. So in this case, we are considering this is an enclosed fluid. In that case, we are exerting the pressure at this side. So the same pressure is distributed in all the direction, and this piston, it is moving outward direction. So this is general example for Pascal's law. In this case, that pressure is distributed uniformly in all the direction. So in next case, we are going to consider a spherical vessel and it is fitted with a 4 frictionless piston. Okay, see here. So consider this is a spherical vessel and it is fitted with 4 frictionless piston. So this is the first. Okay, see here. So this is a spherical vessel and it is fitted with 4 frictionless piston. So this is a piston P1 and this is a piston P2 and this is a piston P3 and this is a piston P4, right? Okay. So and this vessel is filled with some liquids. Okay. See here. So in this case, the area of a cross section of the first piston, so that is A1, area of a cross section of a second piston A2, area of a cross section of a third piston, that is A3, and the area of a cross section of a fourth piston is A4, right? Okay, see here, this is a spherical vessel and this vessel is filled with the 4 frictionless pistons of a different area of a cross section. The area of a cross section of the first piston is A1, second piston is A2, A3 and A4, right. So afterwards we are going to apply some amount of force. Here we are going to apply some amount of force F1 on the piston P1. So due to this force, that piston move in downward direction. Due to this force, the piston move in a downward direction. In that case, this piston, it exerts some amount of pressure on the fluid, right. So in this case, this piston exerts some amount of pressure on the fluid. So that pressure is distributed uniformly in all the direction. That pressure is distributed uniformly in all the direction. Due to that pressure, the remaining 3 pistons are moving outward direction. Okay, so here in this case we are exerting the force F1 on the piston P1. Due to that force, that piston is moving in the downward direction. So after that, this piston exerts some amount of pressure on the fluid. That pressure is distributed uniformly in all the direction. Due to that pressure, the remaining 3 pistons are moving outward direction. Okay, if you want to keep the piston for their respective position or their own position or their original position, in that case we are going to apply some forces on the piston P2, P3 and P4. So here, if you want to keep the piston their respective position, we have to apply some amount of force, that is F2 force on the piston P2, F3 force on the piston P3 and F4 force on the piston P4. So then the pressure at all the point is same. Here the pressure at piston P1 is, that is F1 by A1, that is equal to the pressure at the piston P2 is, that is F2 by A2, and the third one is the pressure on the piston P3 is F3 by A3, on piston P4 is, that is F4 by A4. So then F1 by A1 is nothing but the pressure. So pressure at the piston P1 is also same. P1 is equal to P2 is equal to P3 is equal to P4, right. So this indicates that the pressure at any point is same. The pressure at any point is same. Okay, see here. In Pascal's law, the statement is, if an external pressure is applied to any enclosed fluid or liquid, is transmitted uniformly in all the direction. So in this case we are consider a spherical vessel. It is fitted with a 4 frictionless pistons of a different area of a cross section, and this vessel is filled with some fluids, right. So here we are going to apply some force F1 on the piston P1. Due to this force, that piston move in downward direction. In that case, this piston exerts some amount of pressure on a fluid. That pressure is distributed uniformly in all the direction. Due to that pressure, the remaining 3 pistons are moving outward direction. To keep the 3 pistons in their respective position or in their original position, we have to apply some amount of force, that is F2, F3 and F4 force on the piston P2, P3 and P4. So then the pressure at all the pistons are same. So here the first pressure on the first piston is, that is F1 by A1, that is equal to F2 by A2, that is equal to F3 by A3, that is equal to F4 by A4. It indicates that the pressure at piston P1 is also same, P2 is also same, P3 is also same and P4 is also same. From this one we are concluded that if we apply the external pressure to any enclosed liquid, it is transmitted uniformly in all the direction. The next one, applications of Pascal's law. In that first one is hydraulic lift and the second application is hydraulic brake. So first we will discuss about hydraulic lift. So here hydraulic lift, it is works on the principle of Pascal's law. So with the help of a small force, we can lift very heavy object, right. Okay, see here, the hydraulic lift, it consists of 2 cylinders of different area of a cross section. This is a first cylinder A and this is a second cylinder, that is B, right. So in this case, the area of the first cylinder is, that is A1, area of a second cylinder is A2. And these 2 cylinders are connected with the help of a horizontal pipe, right. So in this case we are consider the two cylinder A and B of different area of a cross section. Here the area of a first cylinder is A1 and the area of a second cylinder is A2, and these two cylinders are connected with the help of a horizontal pipe. After that, for these two cylinders we are fitted a frictionless piston. So this is a piston P1 and this is a piston that is P2. Okay, so this is a piston P1 and this is a piston that is P2, right? So afterwards we are filled these cylinders with some fluids, this cylinder with some fluids. Okay, see here, this is the construction part. So in construction part, the hydraulic lift consists of a two cylinder A and B of a different area of a cross section, and it is filled with some liquids or fluids and fitted with a piston P1 and P2. Here the condition is the area of a second cylinder, it is greater than the area of the first cylinder. Okay, in this case we are going to apply some amount of force, F1 force on the piston P1. So due to this force, the piston is moving in downward direction. Due to this force, the piston it is moving in downward direction. In that case, this piston exerts some amount of pressure on the fluid. See here, in this case, this piston exerts the pressure, that is F1 by A1 on a fluid, right? So according to the Pascal law, this pressure is distributed uniformly in all the direction. This pressure is distributed uniformly in all the direction. So afterwards, this fluid exerts a pressure on a piston P2. Due to that pressure, this piston move in upward direction. This piston move in upward direction. So this is the working of a hydraulic lift. Okay, see here, in this case, we are applying the small amount of force F1 on the piston P1. Due to this force, this piston is moving in a downward direction. In that case, this piston exerts some amount of pressure on a fluid. That pressure is distributed uniformly in all the direction. So after that, this fluid exerts some amount of pressure on the piston P2. Due to that pressure, this piston is moving outward direction. This piston P2 it is moving outward direction. So next one, we are going to find out the how much of a force exerting on the piston P2. The force on piston P2. So here the force on the piston P2 is, that is F2 is equal to the pressure exerted by the fluid here. The pressure is, that is F1 by A1 into area, that is A2. So this is the formula we are used to find out the F2 force acting on the piston P2. So that F2 is equal to F1 by A1 into A2. If you want to find out F1 force, so then F1 is equal to, that is F2 by A2 into A1. So this formula we are used to find out the F1 force, right? So in this case, this formula we are used to find out the force exerting on the small piston. The next application is hydraulic brake. The first application is hydraulic lift. It is works on the principle of a Pascal's law. With the help of a small amount of force, we can lift heavy object, right? So the second application is hydraulic brake. And this is a schematic diagram for the hydraulic brake. So in hydraulic brake, it is also consists of a two cylinder. The first one is a master cylinder and the second one is the slave cylinder. So here is also the area of a slave cylinder is more comparing to the area of the master cylinder. And these two cylinders are filled with some fluids. Okay, see here, this is the brake pedal and this is the brake pads and this is a large disc and this is a tire, and this is a axle, and this one is the slave cylinder. Okay, see here, in this case we are exerting some amount of force on the brake pedal. So we are exerting some amount of force on a brake pedal. Due to this force, this piston is moving inward direction. This piston is moving inward direction. In that case, this piston, it exerts some amount of pressure on the fluid. That pressure is distributed uniformly in all the direction. That pressure is distributed uniformly in all the direction. So afterwards, this fluid, it exerts pressure on the brake pads. So see here, consider this is a brake pad. So in this case, the fluid is exerting the pressure on the brake pad in this direction. In that case, this brake pad is moving in outward direction. Okay, see here, it is very simple. So in this case, we are applying some amount of force on the brake pedal. Due to that force, this piston is moving the inward direction. So here, this piston, it exerts some amount of pressure on the fluid. That pressure is distributed uniformly in all the direction. So afterwards, so consider this is a brake pad. So here, this fluid, it exerts a pressure on the brake pads. Due to this pressure, this brake pad is moving in outward direction. It is moving outward direction. Due to the friction between this brake pad and the large disc, the vehicle comes to rest. So this is the working of the brake pedal. Right? It is also very simple. It is the one of the applications of a Pascal law. According to the Pascal law, if the pressure is applied to any enclosed liquid, it is transmitted uniformly from all the direction. So in this case, we are applying the force on the brake pedal. Due to that force, the piston is moving inward direction. This piston exerts some amount of pressure on the fluid. That pressure is distributed uniformly in all the direction. So afterwards, this fluid exerts a pressure on the brake pads. So these brake pads are moving in outward direction. Due to the friction between the circular large disc and the brake pads, the vehicle comes to rest. See the problem here. A car of mass is 3000 kg is to be lifted by a hydraulic lift as shown in the figure. The area of a cross section of the piston carrying car is 15 centimeter square, and the area of a smaller piston is 10 centimeter square. Calculate the force needed to be applied on the smaller piston to lift the car. Okay, see here in this case they are given the mass of a car is given, that is 3000 kg, and the area of a larger piston, so that means A2 is equal to 15 centimeter square. Convert into meter square, then 15 into 10 to the power is minus 4 meter square. Next, area of a smaller piston, that is A1 is equal to 10 centimeter square. Convert this into meter, that is 10 into 10 to the power of minus 4 meter square. And here the force F2. So F2 is nothing but it is the mass into acceleration due to gravity. Here the mass of a car is given, that is 3000 kg into acceleration due to gravity, so that is 9.8. So this is the F2 value. So then we are going to find out what is the force we have to apply on the smaller piston to lift the heavy object, right? So already we know that the formula to calculate the force F1, so that is F1 is equal to F2 by A2 into A1, F2 by A2 into A1. Here we are going to find out the F1 value, F1 as it is. So F2 value is nothing but mass into acceleration due to gravity. So that is mass of the car is 3000 into acceleration due to gravity value is 9.8, and the area of a larger piston, that is 15 into 10 to the power is minus 4 into area of a smaller piston is, that is 10 into 10 to the power is minus 4. 10 into 10 to the power is minus 4, right? Okay, in this case 10 to the power of minus 4 and the 10 to the power of minus 4 both are get cancelled. The remaining is, that is F1 is equal to 3000 into 9.8 into 10 divided by 15 divided by 15. So here 3000 into 9.8 into 10 divided by 15, that is equal to 19600 Newton. So this is the final result of this problem, right? So in this case we are going to find out the force applied on a smaller piston. Its value is 19600 Newton. So in this problem they are given, mass is given, area of a larger piston given, area of a smaller piston is also given. We have to find out the F1 value, right? So F1 formula is F1 is equal to F2 by A2 into A1. F1 is equal to F2 value is mass into acceleration due to gravity 3000 into 9.8 into A1 value 10 into 10 to the power is minus 4 divided by 15 into 10 to the power is minus 4. Here minus 10 to the power of minus 4, 10 to the power of minus 4 both are get cancelled. The remaining is F1 is equal to 3000 into 9.8 into 10 divided by 15, that is equal to 19600 Newton. See here, the next concept is fluid dynamics. So fluid dynamics means it is a branch of fluid mechanics. It deals with a fluid is in motion. So that is known as the fluid dynamics, right? So in fluid dynamics there are three types of flows. The first one is a streamline flow, turbulent flow, and the last one is a laminar flow. The first one, what do you mean by the streamline flow? So streamline flow means the regular flow of fluid, that is known as the streamline flow. The regular flow of liquid or fluid, that is known as the streamline flow. Or the velocity of the particle at any point is the same, so that flow is also known as the streamline flow. Okay, see here, in this case we are going to consider, so this is a bend shaped tube. Consider this is a bend shaped tube. So this is first phase of the tube and this is the second phase of the tube. So in this case the area of a first tube is A1, area of the second phase, that is B, is A2. So in this case the liquid or the fluid, it is enter at point A and exit at point B, right? So the liquid, it is enter at point A and it is exit at the point B. In this case we are going to consider the some points. So consider this is a point A and this is a point B and this is a point C, right? So in this case the velocity of the particle at any point is the same. For example, consider this is the first particle, this is second particle, this is the third particle and this one is the fourth particle. If the first particle, this first one, second one, third one and fourth particle, if the first particle it reaches at point A, in that case its velocity is v1, and the second particle if reaches at point A, in that case also its velocity is v1. If the third particle it reaches at point A, its velocity is v1. Similarly, if the particle A it reaches at B point, its velocity is v2. If the second particle, third particle and the fourth particle, if it reaches at the point B, in that case its velocity is v2. Similarly, if first particle, second particle, third particle and the fourth particle, if it reaches at point C, its velocity is v3. So this indicates that the velocity of the particle at any point is same. So that is known as the streamline flow. Streamline flow means the regular flow of fluid, so that is known as streamline flow. Or if the velocity of the particle at any point is the same, so that is also known as the streamline flow. So then the characteristics of the streamline flow, if you want to find out what is the direction and what is the velocity of a particle at point A, at point B and at point C, for that one we have to draw a tangent to this point. If you draw the tangent to point C, that gives the velocity and the direction of the particle at that point. If you draw the tangent, to this point, that gives the velocity and the direction of the velocity of the particle at that point. The first characteristics of the streamline flow is, so that is, if you draw tangent to any point, that gives the magnitude and the direction of a velocity of the particle at that point. So this is the first characteristic, right? It is very important. And the second characteristic there is no two streamline flow can cross each other. There is a no two streamline flow never cross each other. So that is the second characteristic, right? Okay, see here, for example, consider this is a one streamline flow and this is another streamline flow. So here at the point of intersection, the streamline flow, it having the two direction, it is not possible, right? In this case, if you want to find out what is the speed of the or what is the velocity of the particle at this position, so in this case, if you draw the tangent at this point, this gives the direction of this one. If you draw the tangent at this point, this gives this the direction. So it is not possible, right? So the second characteristic is no two streamline can cross each other. The very important characteristic. The first characteristic is if you draw the tangent at any point, that gives the direction and the magnitude of the velocity of the particle at that point. And the second characteristic is no two streamline can cross each other, right? So streamline flow means regular flow of fluid or the velocity of the fluid at any point is same. So that is known as the streamline flow. The second one is turbulent flow. So what do you mean by the turbulent flow? So turbulent flow means it is irregular flow of fluid. It is a irregular flow of fluid. It is exactly opposite to the streamline flow. In a streamline flow, there is a regular flow of fluid, that is known as a streamline flow, and the velocity of the particle at any point is same, that is also known as a streamline flow. So turbulent flow means it is irregular flow of fluid. It is a irregular flow of fluid. The velocity of the particle at any point is not same. So that flow is known as the turbulent flow. That flow is known as the turbulent flow. What is the simple definition for the turbulent flow? The irregular flow of fluid. So that is known as the turbulent flow. And the last one is a laminar flow. Last one is a laminar flow. Okay, see here, in this case, this is a horizontal surface. If the liquid is flows on a horizontal surface, if the liquid is flows on the horizontal surface, in that case, it forms different layers. It forms different layers. And these different layers are moving with a different velocity. Different layers are moving with a different velocity. So that is known as the laminar flow. So what is the definition of a laminar flow? If a fluid or a liquid, it is flows on a horizontal surface, it forms a different layers. It forms different layers and different layers are moving with a different velocity. So that flow is known as the laminar flow, right? So these are the three types of a flow. First one is streamline flow, turbulent flow, laminar flow. Streamline flow means regular flow of fluid, turbulent flow means irregular flow of fluid, and the laminar flow means if the liquid is flows on a horizontal surface, it forms a different layers. Different layers are moving the different velocity. So that is known as the laminar flow. The next concept is equation of continuity. The next concept is equation of continuity. So in this case, we are going to consider a bend shaped tube. Consider this is a bend shaped tube of different area of a cross section. So this is a first face, that is A. Area of a cross section of the first face is, that is A1, and this is the second face, that is B. Area of a cross section, that is A2, right? So in this case, if the liquid is enter at point A and it is leaves at point B, right, with some velocity, the velocity at A point is V1 and the velocity of the fluid at point B, that is V2, and the density of a fluid, so here this is rho 1 and this is the rho 2, right? So in this case, we are going to consider a bend shaped tube of a different area of a cross section. So this is the first face A and this is the second face B. So here A1 indicates that the area of a cross section of at point A, and A2 indicates that the area of a cross section of the tube at point B, right? And here rho 1 and rho 2 indicates that the density of the fluid, and V1 and V2 indicates that the velocity of the fluid enter at point A, and V2 indicates that the velocity of a liquid, it is exit at a point B, right? Okay. The first one, we are going to find out the distance traveled by the fluid at a point A in a very small time interval, that is del of t. So first one, we are going to find out the distance traveled by the fluid at a point A in a small time interval del of t, that is equal to the distance traveled by the fluid at a point A in a small time interval del of t. Here already we know that the velocity is equal to distance by time. So in this case we want the distance is equal to velocity into time. Okay, so here the distance traveled by the fluid at point A in a small time interval del of t, that is equal to, here the velocity of the fluid at point A is v1 in a time interval of del of t. So then the distance traveled by the fluid at a point A in a small time interval, that is del of t, that is equal to v1 into del of t, So this is our equation number 1. So next, the mass of the liquid, that is crossing of area of a cross section A1 in a small time interval. The mass of the fluid crossing at a point A in a small intervals of time, del of t, that is equal to. So already we know that the definition of a density is equal to mass per unit volume, then mass is equal to density into volume. So in this case, volume can be written as area into distance traveled by the fluid in the tube. Okay, see here the mass of the fluid crossing at point A in a small time interval of del of t, that mass is equal to density of the fluid at point A is, that is rho 1, and the volume can be written as area of the first phase is A1, and the distance traveled by the fluid at point A in a small time interval, that value is v1 into del of t, Okay, see here, in this case the mass of the fluid crossing at point A in a small time interval of time del of t, that is equal to, so formula is density into volume. So volume can be written as area into distance traveled by the fluid. Here mass is equal to, first one density, the density of the fluid at point A is, that is rho 1, and the area of a cross section of the first phase is A1. Next, distance traveled by the fluid at point A in a small time interval del of t, that is v1 into del of t. So then mass value is rho 1 A1 v1 into del of t. So next one, similarly the distance traveled by the fluid at point B, in a small time interval is, that is v2 into del of t, right? Okay, see here the distance traveled by the fluid at point B in a small time interval del of t, that is equal to v2 into del of t. V2 into del of t. So after that, the same, the mass of the fluid crossing at point B in a small time interval. The next one, the mass of fluid crossing at point B in a small time interval del of t. In a small time interval del of t, that is equal to, here m2 value is same, density into area into distance travelled. Here the density is ρ2 and the area is A2. The distance travelled is, that is V2 into del of t. V2 into del of t. Okay, see here. This one is the mass of the fluid crossing at point A, is value is ρ1 A1 into V1 into del of t. Similarly, the mass of the fluid crossing at point B in a small time interval, that is ρ2 A2 V2 into del of t. Okay, see here, in this case, if the same amount of liquid it is enter at point A and the same amount of liquid or the fluid it is exit at point B. So from this one we are going to equate this equation number 2 and equation number 3. Okay, see here, in this case the same amount of fluid is enter at point A and the same amount of fluid is exit at point B, right? So from this one we are going to equate the equation number 2 and equation number 3. And the one more thing here, if the same liquid is enter at point A and the same liquid is exit at point B, so then the density of a liquid or the density of a fluid is same, that is ρ1 is equal to ρ2 is equal to ρ. Okay, see here, they equate these two equation here. The equation 2 is ρ1 A1 V1 into del of t, that is equal to ρ2 A2 V2 into del of t. So in this case the same liquid is enter at point A, the same liquid exit at point B, then ρ1 ρ2 is equal to ρ. So ρ into A1 V1 del of t, that is equal to ρ A2 V2 del of t. Ρ A2 V2 del of t. So in this case density both are get cancelled, del of t both are get cancelled. What are the remaining equation here? That is A1 V1 is equal to A2 V2. Okay, so here I will write here, that is A1 V1 is equal to A1 is equal to A2 V2. So here A1 indicates that is the area of a cross section of a first phase, and V1 indicates that the velocity of a fluid at point A, and A2 indicates that the area of a second phase of the tube, and V2 indicates that is the velocity of a fluid at point B. So in general AV is equal to constant. In general AV is equal to constant, or velocity is inversely proportional to area. Velocity is inversely proportional to area. Okay, see here, if the area of the tube is more, the velocity of a fluid at that point is less. If the area of the tube is very less, in that case the speed of the fluid exit from the point B, it is more, right? So here the velocity is inversely proportional to area. If the area value is small, the velocity is large. If the area value is large, then the velocity is small. So this is the equation of continuity. So in equation of continuity, first we are consider a bend shaped tube. It consists of two phases. This is first phase and this is second phase, and here the area of a first phase is A1 and the area of a second phase is A2, and V1 and V2 indicates that the velocity of a liquid is enter at point A and the velocity of a liquid exit from the point B. And here ρ1 ρ2 indicates that the density of the fluid enter at point A and at exit at point B. The first point is the distance travelled by the fluid at point A in a small time interval. Its value is V1 into del of t. This is our equation number 1. After that, the mass of the fluid crossing at point A in a small time interval del of t, that is equal to density into volume. It can be written as density into area distance traveled by the fluid in a small time interval. Its value is rho 1 A1 V1 del of t. Similarly, at point B, that is distance traveled by the fluid at point B in a small time interval, V2 into del of t. The mass of the fluid crossing at point B in a small time interval del of t, that is also same, rho 2 A2 V2 del of t. So this is our equation number 3. If the same amount of liquid is enter at point A, the same amount of liquid is exit at point B. So from that one, we are equating the equation number 2 and equation number 3, right? We are equating equation number 2 and equation number 3. So here, the same liquid is enter at point A and the same liquid is exit at point B, means the density of the liquid is same. Here the density rho 1 rho 2 is equal to rho. So then substitute rho 1 value is rho 2 value is rho. Here rho get cancelled, del of t both are get cancelled. What are the remaining terms here? A1 V1 is equal to A2 V2. A1 V1 is equal to A2 V2. In general, AV is equal to constant. In general, AV is equal to constant, or V is inversely proportional to area. V is inversely proportional to area. So it indicates that area is small, velocity is large. If area is large, velocity is small. Thank you.